So, in this session we are going to learn about lenses, not a single lens. So, combination of lenses and some non-standard problems on these lenses. So, let us first see the lens equation. Previously we have used 1 by V minus 1 by U is equal to 1 by F. Now, Newton's equation for the image formation by thin lens. Now, suppose this is a lens, thin lens. So, I can neglect this, and here we have an object here, object of some height here, and this is the focus F. So, if parallel rays are coming from this side, they will converge here. So, focus for this lens from this side is here, and suppose if the parallel rays are coming here, they are focused at some point, suppose F dash. So, this is F dash. This is AB, the object whose distance from this is x, and let us call this as F. So, any ray parallel to this passes through this focus here like this, and any ray passing through this, will become parallel, because any ray parallel will meet at this side the focus. So, this is F, this is F dash, and this distance will be also F dash, F dash. This is the image, this is AB with height y, and this is A dash, B dash with height y dash. So, now you see here, this is a right angle and this is a right angle. This angle is equal to this. So, these two triangles are similar. So, if we consider these two triangles similar, then this, you see, this ray is parallel to this optic axis. So, if this is y, this is y dash. So, this is also y dash. So, you see y by y dash is equal to x by f. So, from these two similar triangles, y by y dash is equal to x by f. This is equation number 1 from these two triangles. Similarly, consider these two triangles. This line is parallel to the optic axis. So, this is y. So, this will be also y, and you see this is opposite vertical angle, this is right angle. So, this triangle and this triangle is equiangular. So, again we will get from this triangle y and from this triangle y dash, y by y dash is equal to this, that is f dash by, suppose I call this distance is x dash. So, here you see this object is measured, its distance is measured not from this pole but from this focus, and here image, this distance is measured from this point. So, these two equations are there. From 1 and 2, we get what we do, this x, y by y dash and y dash is common. So, we have x by f is equal to f dash by x dash, implies x dash is f dash, x dash is equal to f dash. This is what Newton's formula. So, this formula can be used just like 1 by V minus 1 by U is equal to 1 by F, where all the distances are measured from this place, but for this formula, this all the distances means object distance is measured from this focus, image distance is measured from this focus. So, x dash becomes f dash formula. So, now come to Smith-Helmholtz formula or Lagrange invariant. This is popularly known as Lagrange invariant, and this formula is very helpful for the design of zoom lenses, where there are many optical systems, many lenses, combination of lenses. So, when we have to calculate the net magnification produced or the magnification or image size in the middle or in the mid of a large component of lenses or at any place, then this Lagrange invariant formula is very helpful. So, in order to first see, let us see that if we have a lens, suppose I take a single lens and it separates two media, one of refractive index n and another of refractive index n dash. So, it may be a lens or just suppose it is not a lens but a refracting surface. Suppose it is a refracting surface and here we have an object AB of height y. Now, because of this refracting surface, suppose there is a image formed here. Suppose consider a paraxial ray, this goes to C and which again falls here D, and here we get a image, we may get image here or here, we do not know. So, this ray makes an angle theta, this and this angle theta dash. So, if this is theta measured from here and it is measured here, you see you will get an image, suppose this is y dash. So, this is AB, this is CD and call it E. Now, this is theta and this is theta dash, this is n and this is n dash. Then let us consider this triangle and apply sine rule. So, applying sine rule in the triangle BDE. So, BE sine theta by ED is equal to sine theta dash by BE. Now, since these angles are small, so sine theta can be approximated as theta and ED is nearly equal to this, so this can be written as V. Next, sine theta dash, this angle is theta dash, can be approximated as tan theta, sine theta dash only, and BE is this distance which is very near to this, so that can be U. So, we have one relation. Now, we define the magnification due to this surface, already we have defined as M is equal to y dash by y is equal to n by n dash V by U. N by n dash V by U. Now, V by U is here n by n dash, V by U is theta by theta dash, implies, now you see y dash, that is y n theta is equal to y dash n dash theta dash. So, this formula, that means if there is not a one system, this is a lens system or this is a composite system, one system, then two system, then three system, then four system. What Lagrange invariant tells that in any system, the height y into the refractive index and the sine and the angle the paraxial ray subtends with this is going to be constant, will remain constant. Whatever may be the number of lenses, out of all, suppose there are 4-5 system, final also you can take in any medium. That means after in the middle of the lens system, anywhere you can use this expression, that is y n theta is equal to y dash n dash theta dash. You see, this is not a proof, I have just justified with the case, with an example that this will be a constant, but this can be generalized and this will be highly helpful in a complicated network of lenses. Let us see with an example. Now, suppose we have a problem like this is one lens system and there is another lens system, two lens system L1, L2, its F1 and F2 is given. So this is the object position. So what we do, we take a ray, then it goes and finally its image is formed like this. So first image is formed here. So if we have an object of some height, here is also an image formed and here all. So final magnification will be given as M1 into M2. M1, suppose this is U, this is V1, M1 is given by V1 by U, and suppose this is U2 and this is the final V. So M2 is given as V by U2, and the product of this, you see, M1 M2 gives V1 by U into V by U2 V this, and so we will get V by U. So the magnification will be given by this, but the problem will be here. So this is the standard method we used to follow. We calculate individual magnifications M1 and M2, and the total magnification is given by the product of M1 and M2. Now suppose this object is kept at infinity, then M1 becomes V1 by infinity and this becomes 0. And so visualizing the magnification when the object is at infinity or focus becomes very difficult. So in such cases we will use that Lagrange invariant formula we will use. So let us take an example. So now let us see this problem. Here we have a convex lens of focal length 10 centimeter and a concave lens of focal length minus 15 centimeter. They are spaced at a distance of 5. Here we have an object at 10 centimeter. So you see, this point is the focus. So any ray going like this goes parallel to this, and then again you see this line is parallel, this ray is parallel, so it will diverge so that it seems to be coming from the focus. So its focus is also this 5 plus 10 is O. So the ray goes like, so you see here the object and the image coincides. Now when the object and the image coincides, if this is a point object, then the image will fall on itself. But if we have an object here of some height, how much is the magnification that we have to calculate? So we will use, according to Smith-Helmholtz formula, that is y n theta is equal to y dash n dash theta dash. So here all the medium except these two has a refractive index different. So this is here 1 and here 1, here 1, everywhere 1. So y is y into 1 into theta. Now suppose this is a ray, this is the incident ray. So how much is the angle subtended by this ray on this lens system? So this theta will be here, suppose I say this distance is y, or let us call it delta. This distance is delta. So this is delta. Delta by F1 is equal to y dash. Suppose the image height formed after this is y dash. So y dash n dash is 1 into theta dash. How much angle theta dash it subtends here? That is given by delta by this F2, that is 15 actually. So delta cancel, implies magnification is y dash by y. Y dash by y. Magnification is y dash by y. So that is F2 by F1. Whether magnification is positive or negative will be decided by the angle made by this ray and this ray, the final ray. So you see both these angles are in the same sense, anti-clockwise. If one is clockwise, another is anti-clockwise, then magnification is -1. So F2 is 15 and f1 value is 10, that is the magnification becomes 1.5. So, if object height is 1 centimeter, the image height will be 1.5 centimeter. So, you see here in this problem the normal methods fails and we get a very easy and convincing solutions by using Helmholtz-Smith formula or Lagrange invariant method. So, you see this formula that y and theta is equal to y dash n dash theta dash remains constant, easily gives a quick solution to the problem. Let us take one more example. So, now let us see another example. We have a lens, converging lens of focal length f1 given by 20 cm, then concave lens of focal length minus 10 cm, they are displaced by 15 cm. We have an object at a very large distance of 0.5 cm height and it is at infinity. So, the question is, where is the final image formed and what is the size of the image? So, what we do? We consider a ray parallel to it. Since the object is at infinity, let us take a ray parallel to the optics axis coming from the object. So, this ray is going to be focused at the focal f1, that is 20 centimeter, that is 5 centimeter from here. This is 5 centimeter. So, this is going to be focused up to this point. So, this is the first image formed by this. But next, this is the diverging lens whose focal length is 10 centimeter. So, you see this is 15 centimeter and its focal length is minus 10 centimeter. So, we have to see where is the final image formed. So, it will go like this. It will bend to the final position. Let us first calculate what is the position of I. So, using lens formula for L2, the second lens, this lens, 1 by V minus 1 by U is 1 by F. 1 by V, V has to be determined. U is here this distance, that is, this is 20, this is 15, so this is only 5. So, 5 centimeter. So, this is 5, so plus 5 and focal length, the rays are coming, so its focal length is here minus 10. So, it will be minus 10. So, 1 by V is equal to 1 by 5 minus 10, that is 10, 2 minus 1. So, V is equal to 10 by 1, that is 10 centimeter. So, we got that again 5 centimeter from here, that means 5 plus 5, 10. So, the final image is formed at a 10 centimeter from here, the ray will go. Now, you see here, this angle is, suppose theta, this is the first angle theta, that means this ray here makes an angle theta after with the optic axis and the final ray makes an angle theta dash. So, using Lagrange invariant, using Smith Helmholtz formula or Lagrange invariant, whatever you call, we have n h theta is equal to n dash h dash theta dash. You see these two are 1, so we need not bother. H is 0.5 centimeter. Theta, what is the angle? This angle theta. So, you see, suppose I say this is also h. So, this theta is h by f1. H by f1 is equal to, now you see this two triangles, this is 5, this is, suppose we have y. Let us use Smith Helmholtz formula, that is n h theta is equal to n dash h dash theta. Since n and n dash are same, so this will cancel out, everywhere refractive index is 1. H is 0.5, let it be h. theta is equal to h dash theta dash. Now let us relate theta and theta dash. So you see this triangle, this y is equal to this r theta, that is 5 into theta, that is equal to, from this 5 plus 5, 10 into theta dash, implies theta by theta dash is equal to 2 by 1. So we got theta by theta dash as 2 by 1. So h dash is equal to h theta by theta dash, that is h into theta by theta dash is 2. So 2h. So h is 0.5 cm. So we have 1 cm object. So magnification theta by theta dash, here we got 2. So thus you see how easily we calculated the final image height by using Helmholtz-Smith formula or Lagrange invariant. So for this type of complicated problems, where if the object is at infinity or at focus, calculation of magnification due to individual lens becomes difficult. So in such cases we use Helmholtz-Smith formula or Lagrange invariant. So now let us take another example where two lens system is used here. This is a converging lens of focal length f1. This f1 is greater than d. This has a focal length f2. This lens both are converging, focal length f2, and its optic axis is displaced by the optics axis of the first lens by this delta. We have to find the coordinates where these rays, parallel rays from the extreme left end will converge. So that coordinates we have to calculate, and this is our y axis and this is the optics axis is x axis. So that means this is my origin 0, 0. So because of this lens, suppose the focus is here, this point is f1, that means this ray is going to be focused at this place. This ray will be focused at this point. This is focus. But actually here the rays will again bend and form an image I here. So the rays here will finally converge due to this lens at this place I, and we have to find the coordinates of this point. So what we will do, because of this lens, for this lens the object is this f1 and this is a virtual object. So what is this distance? This distance is f1 minus d. So this point, this this total distance is f1, let this point be called as P. So the point P where these parallel rays should have converged acts as a virtual, the point P acts as a virtual object for the lens L2 using lens formula. So 1 by V minus 1 by U is 1 by F2. This F2. What is 1 by V? V means this distance, this position, this is V. This we have to determine. So 1 by V is equal to 1 by F2, this plus 1 by U. What is U? U is F1 minus D. So you see, if we add up, we get F2 F1 minus D, that is F1 minus D plus F2. So we have V is equal to, this V becomes F2 F1 minus D by F1 plus F2 minus D. This is V. This is V. So I got this position of I, final image from this lens, and this x coordinate will be D plus this one. Now what is its y coordinate. So you see, in order to know its position, you just imagine that this is the object height. So if this is an object here, so its image is formed here. So magnification, so suppose I say this height is, suppose this is denoted by y dash. So this is y dash and this is by y is here delta. So the magnification will be given by this y dash by this delta is equal to v by u. Now v is this much and divided by u is f1 minus d. So v, this is equal to magnification, that is v, this divided by f1 minus d becomes f2 by f1 plus f2 minus d. So thus you see we got y dash is equal to f2 delta by f1 plus f2 minus d. This is y dash. So you see, now I got the coordinates of I. So coordinates of I is given by xy, whose x coordinate is given by d plus this, d plus v, that is d plus v. I will write simply v is this much, and its y coordinates will be delta minus y dash. So that is delta minus y dash, where y dash is given from this. So y dash we know, we will put here, and so this is the final focus due to this combination. So all the parallel rays from left is focused. So you see here what happens when one of the optic axis is displaced above. So this is how the image formation takes place. Now let us take an example where this is a lens of focal length f, converging lens, and at a distance 2f we have placed another lens, identical lens, but this time its optic axis here you see is changed, rotated by 60 degree. So two identical lens separated by 2f, but its axis is rotated by 60 degree. Now we wish to calculate if we have two parallel rays coming from here, where the final image is formed. If we have a distant object here, where is the final image formed by this combination of lenses. So you see here, this is 2f, between these 2 points the distance is 2f. So the rays will converge here at this place and form an image here. This is the first image I1. Now this distance is f, so is this distance f. Now the distance of I1 from this lens cannot be considered at f. We drop a perpendicular here, the distance will be this much, that is f cos 60 degree. Cos 60 degree is half, so that becomes f by 2. That will be f by 2. Cos 60, that is f by 2. So we got this distance as f by 2. Now when you see, the distance is to be always measured along the optic axis. So when the distance is f by 2 less than f, so you will get some magnified image somewhere here. One more thing, image will be always formed on the line, because you see this is the ray which passes through the optical center. So the image will be formed on this line only, because this ray will be also used for image formation, and since it is going to be undeviated, so on this line somewhere image will be formed. So let us calculate this position. This position, how much is this distance from this? So using lens formula, 1 by v minus 1 by u as 1 by f. 1 by v, object distance is minus f by 2. So this becomes f by 2, 1 by f, implies 1 by v is 1 by f minus 2 by f, that is minus 1 by f, implies v is equal to minus f. So v is equal to minus f, minus means this side, that means this distance becomes f. So if this distance is, so what is this distance? Let this be x. So this f is equal to x cos 60 degree, that is f is equal to x cos 60 means half, so x is equal to 2f. Now 2f means x is this point. So what we got mathematically is that the image is formed on here. So what we have learnt, number 1 point, the image, the object distance should be always calculated along the optic axis. So this distance is f, but its object distance will be calculated as f by 2. So that's x. So let us first write down this, and now we will draw its ray diagram to see how the final image is formed at this point. Please take it. So now you see here the ray diagram for this. Suppose the rays are parallel, then they pass through the focus. So they pass through the focus, and then again they bend in such a way that they seems to be coming from here. So you see here, this is the final image, that is the virtual image formed due to the combination of lenses. This is the first image I1 and this is the final image I. That is the virtual image if we see from that side. This is the ray diagram. So now in the experimental physics portion of IIT, on this topic we have to find the focal length of a convex lens by plotting graphs between u and v, and between 1 by u and 1 by v. So this is experiment in our IIT portion. So here, just like the mirror, we take an optical bench, and on an optical bench we place a lens. We will place now object at certain positions, object, and corresponding to a fixed position of object, corresponding to a position, we will find v, and we will take readings of u and v, 4-5 readings, and then we have to plot u and v graph and 1 by u and 1 by v graph, and from the graph we will see how to determine the focal length of the converging lens. So let us first see the theory used in the problem. So here lens formula gives 1 by v minus 1 by u is equal to 1 by f. For a lens we will use x for u and y for v. So what we will do, we will use this x and y for this. So we have 1 by this v as y, minus 1 by x is 1 by f, the focal length. Now for a convex lens, the focal length is positive. So now let us simplify it. This is x minus y into f is equal to xy. So xf minus yf, then we bring again minus xy, and then minus f square is equal to f square. So let it be plus only. So now take xf and here x common. If I take x common, I get f minus y, and from this if I take f common, I get f minus y is equal to f square. So you see f minus y is common, x plus f is equal to f square. This is the equation we got. Now let us replace, let us put f minus y as minus y, implies we have y is equal to y minus f, and we will put x plus f is equal to x. Thus the equation becomes f minus y is minus y, that is y into x is equal to minus f square. We got y into x is equal to minus f square. This represents a rectangular hyperbola. This is rectangular hyperbola. Please take down this. Then we will draw the diagram of this rectangular hyperbola. Now you see, let us draw this. This is your y axis and this is the x axis. Capital X, capital Y axis. So this equation, this is the rectangular hyperbola. The asymptotes are here, this x axis and y axis. These are asymptotes, means at infinity they will meet here. We are not interested in this part because object is, we are interested in the real object positions. Now, if I put y is equal to 0, small y is equal to 0, I will get y is equal to minus f. Y is equal to minus f. Y is here minus f. So y is equal to minus f gives this axis, my x axis. X axis means I have to put y equal to 0. Now y axis means if I put x is equal to 0, then x is equal to f. X is equal to f. We got x is equal to f here. So you see, this will represent small y and this will represent x dash, x axis. So x axis will be here and y axis will be here. So you see, for my x and y axis, that is u and v, you see these asymptotes, this point is f and this point becomes f. This distance is f. So this curve goes like this. So you see, for this axis, the curve of that is, first take down, then I will draw only this axis. Please take down this. So let us see here. So I am separately drawing this now. Suppose this is my x axis and this is my y axis. I am plotting u here and v here. So this, I get a curve like this. So I will get a curve like this. So asymptotes are here, these two lines at a distance of f and f. This will be minus f, this will be plus f. So from this frame, this will be looking like this. So we will get this u versus v graph for a convex lens to be like this. So now what we have to do, we have to plot along x dash axis u and along y axis we have to plot v. So plot u and v with equal scale. You see, the scaling should be same both side. So what we will do, we will plot some points. Suppose this is one point, I got u1 v1, then another point u2 v2, another point u3 v3, like that. So we will build up a curve by joining these points. So the points, if the points is more, the curve will be very well shaped. So once I get a curve by just drawing freehand drawing by taking the points, then we draw 45-degree angle with here, which meets here, and this is O. This is A and this is B. So F will be given by this OA by 2 is equal to OB by 2. because this will be 2f, this will be 2f, this will be 2f. So, simply we have to draw perpendicular and measure OA and OB, both will be equal, and so the focal length will be OA by 2, that is equal to OB by 2. Now, another curve for UV. Next, what we do? We draw a equal scale. Along this we plot x dash axis, we plot U, and along y we plot V. The scaling should be same. Now, what we do? Suppose for U1 object position the image is at V1, for U2 it is at V2, for U3 it is at V3, for U4 it is at V4. So, what we will do? We will take up U1 first, U1, then I get V1. So, I will join these two. Then take U2, I will get V2, then I will join these two. So, I get a point of intersection, and if we take another ordered pair, it will be V3 and U3, and all will be like that. So, we will find the point of intersection, and that point is suppose P, then I draw a perpendicular OA, PA and PB on this. So, my focal length will be given by PA, that will be equal to PB. So, this will be F. So, this point of point P has a coordinate F and F. This is minus F this side. So, minus F and F. So, thus this distance and this distance will be equal to P, focal length F. Now, our length formula is 1 by V minus 1 by U is 1 by F. We put 1 by V along y axis and 1 by U along x axis. So, we get y is equal to x plus 1 by F. So, you see this line, suppose I say this is x and this is y, its slope is 1, and 1 by F is here positive. So, its intercept is 1 by F. So, this will be a line like this. We are interested in this part. So, what we do? When we measure U1, V1, then for another object position U2, its image is at V2, then we calculate its reciprocal and we plot its reciprocal. So, this is x axis, this is y axis, here 1 by V is plotted and here 1 by U is plotted. So, what we observe that when I get some readings, then we join all these points. So, when I join these points, they intersect at suppose A and B. So, 1 by F becomes OB or OA, anything we can say, because the slope is 45 and they will be equal. So, the 1 by focal length is given by OB or OA. So, we will have F is equal to 1 by OA or 1 by OB centimeters. So, this is how we plot U, V, 1 by U, 1 by V, and calculate the focal length in our lab.